Hello, good evening. Good evening again. This is our easy lecture series. It's May 11th of May to 2020. My name is Boris Jeremic. Together with me are Mr. Heshen Wang. He's going to talk today about some
Hi.
issues in probabilistic modeling, polynomial chaos, and so on. And Dr. Han Yang, who did presentations before on different topics, and he's going to do some more over the next few weeks. So with this, we'll start. Hesham, please
Okay.
share your screen, and then we can go on and do this lecture online. Thank you. Go ahead.
Okay.
So
Yeah,
share.
I will share my screen.
Yeah.
Okay. Good morning, everyone. Today I'm going to talk about the uncertainty quantification using Hermite polynomial chaos. And this is the outline. So at the beginning, I will give you a brief introduction about the modification of this whole theory. So essentially, it applies in the performance-based earthquake engineering, where you might have some uncertain earthquake source propagating through your uncertain parts and to your uncertain site, and eventually to your uncertain structure system. And you want to design your engineering system or analysis your engineering system to have a acceptably small probability of engineering demanded parameter or damage measure or loss. And for example, a typical engineering demanded parameter that we use might be the interstory drift of different floors of your building. And in order to solve such a problem, we can describe the problem into mathematically into uncertainty quantification. So this is our general equations of the motions. As I mentioned that you might have some uncertainties in your, in your soil site or your building structures that will gives you an uncertain stiffness term to your left-hand side. And also on the other hand, you might also have some uncertain earthquake source propagating through your uncertain parts to your uncertain site that will give you uncertain seismic motion. And these uncertain seismic excitations will also contribute to your right-hand side, the uncertain forcing term. And so eventually we will have a system that have uncertain stiffness and excited by the uncertain random forcing, and that will lead to the uncertain probabilistic structure response. It might be have some probabilistic displacement or probabilistic velocity or probabilistic acceleration. And this problem,
Can I just? I'm sorry. Can I just add one thing?
uh,
So the biggest uncertainties are in the stiffness in material and in the
uh,
loads. There might be small uncertainty in mass and in damping. This is viscous damping,
yeah,
but those are usually very small. So we usually treat those as
yeah,
deterministic. Certainly the biggest uncertainty comes from the elastoplastic stiffness, material behavior
yeah,
essentially, and from the
yeah,
loads.
that's
Go
true.
ahead.
Yeah. Yeah, and this problem is an uncertainty quantification problem. Essentially, we need to solve two tasks. Number one is called uncertainty characterization. Essentially, we need to characterize all these uncertainties in my left-hand side stiffness term and in my right-hand side forcing term. We need to figure out what is the marginal distribution of these uncertainties. What's the type of distribution? What's the mean, the variance, and many other statistics. And also, it might also important to determine what's the correlation of these uncertainties. It is either or fully correlated or have some exponential correlation structure and so on. And once we already characterize these types of uncertainties, then we need to do uncertainty propagation. Essentially, we need to solve this underlying stochastic partial differential equation and need to determine the probabilistic dynamic response. What's the mean, what's the variance, and what's the PDF or correlation of your displacement, velocity, and accelerations. And today we're going to focus on this uncertainty characterization part. And as I mentioned before, we need to characterize your uncertain material parameters. That might be some random variables, distributed in your spatial domain. And their marginal distribution can be either Gaussian or non-Gaussian. For most of the times, it is non-Gaussian because they have some, we need to make sure our material parameter is a positive definite. And these random variables, the different location, they can be either homogeneous or heterogeneous. So overall, we can quantify our material parameter as a marginally distributed Gaussian or non-Gaussian, heterogeneous or homogeneous random field. And for the uncertain ground motions part, it's a random variable at each different and at each individual time, it can be either Gaussian or non-Gaussian distributed. For most of the ground motion, it's a Gaussian process. But for some special case, it can also be non-Gaussian. And these random variables, the different time step, they can either be stationary correlated or non-stationary correlated. But so overall, we can quantify our uncertain ground motion as the Gaussian or non-Gaussian distributed stationary or non-stationary random process. And we can find that actually our material parameter and the uncertain ground motion, they have an identical mathematical structure, which we can regard them as a generalized random field, and we have a generalized coordinate system X. It can be either in spatial domain or be or in temporal domain. And here we are using this theta to denote the uncertainty, and we want to have this random field can be arbitrarily, marginal distribution, can be either Gaussian or non-Gaussian, and also it can be able to have a arbitrarily correlation structure. And for the and in order to quantify this arbitrary marginal distribution, we're going to use the mathematical tools called polynomial chaos expansion. And in order to quantify this arbitrary correlation structure, we will use the technique called Cahulian-Loewe expansion. And today we will start with this polynomial chaos expansion technique. So, this is the formula for the Hermite polynomial chaos expansion. Essentially, for any given random variable of an arbitrary marginal distribution can be represented as a linear combination of a deterministic Hermite polynomial chaos coefficient and the bunch of Hermite polynomial chaos bases. And this Hermite polynomial chaos basis is constructed from an underlying standard Gaussian random variable, which is the zero mean unit variance Gaussian random variable. And this Hermite polynomial chaos is essentially a random function constructed from this standard Gaussian random variable. And it can take many functional form. And the one specific function form that we are using here is the Hermite polynomials function. So eventually it will become a bunch of Hermite polynomial chaos bases and have this recurrency relation. And here denotes the order of the Hermite polynomial chaos that we are using to represent this marginal distribution of random variable. And here you can see a more illustration about the different orders of Hermite polynomial chaos with respect to the underlying Gaussian random variable. And and it has some nice properties of the Hermite polynomial chaos. First of all, it has the zero mean property, which means for any from the first order and above, all the mean of the Hermite polynomials are zero. Yeah, as you can see here, the first order is a constant one, and all the other orders, they have the mean value of this Hermite polynomial chaos are zero. So this is the first property, which is the zero mean property. And the second one is mutually orthogonal. So all the polynomial chaos, when we take any two of them combination and we take the expectation, they will become zero, which means they are orthogonal to each other. And because of this orthogonality, we can calculate the coefficient of the Hermite polynomial chaos. I will explain more in the next slides. So now, how do we find the coefficient of this Hermite polynomial chaos for such a Hermite polynomial chaos expansion? We can first multiply both sides by our PC base omega j, and then we can take the expectation. Essentially, we are calculating in simple mean uh, of this product. And because of the orthogonality, the summation term here will only become a single term where the dummy index I equal to the index j, and from that we can calculate the coefficients dj by such a formula. And for this formula, the denominator is essentially a variance of the J's Hermite polynomial chaos, and can be calculated by this formula. After we analytically evaluate this integral, we can find that actually the variance of the J's polynomial chaos is equal to factorial of J. And for the numerator of this formula, uh, we can numerically integrate this by using any numerical integration scheme. And once we have a representation of Hermite polynomial chaos, we can do a bunch of post processing. First of all, we can calculate the mean of the original random variable. is just we just take the expectation, and it turns out it's only the first term of this expansion. And we can also calculate the variance of this random variable. By the definition of the variance, we can end up, it will end up with this summation of all these Hermite polynomial chaos coefficients squared times the factorial of the j, and sum up from the first term and above. And we can see here, actually, it's the first order and above term will contribute to the variance of the random variable. The first term will contribute to the mean, and the second term and above, which is the first order and above the polynomial chaos, will contribute to the variance. And we can also evaluate the probabilistic density function of this random variable. Since now we have a whole expansion of this random variable on the basis of the standard Gaussian distribution. We can first generate the random samples of the standard Gaussian distribution, and then we can calculate the samples of the Hermite polynomial chaos basis and also the random variable based on these random samples. And then we can estimate the PDF of this random variable by using a kernel density estimation of this samples. And now I will present some examples of this polynomial chaos expansion. Let's start with the first very simple Gaussian distribution with any given mu and standard deviation sigma. And for Gaussian distribution, actually polynomial chaos of order 1 is already sufficient and accurate to capture the whole probabilistic distribution. For such a Gaussian distribution, we can write the expansion of the polynomial chaos x equal to mu plus sigma times the c. And here I'm showing you the original exact input distribution and also the PDF from the synthesized from the polynomial chaos expansion. As you can see here, the first order expansion of polynomial chaos is already totally accurate for the Gaussian distribution. And also, let's move to the log normal distribution. So log normal distribution is a little bit is a non-Gaussian distributed, and for any non-Gaussian distribution, you need at least a PC order 2 or above to to quantify the non-Gaussianality, and it also depends on the variance of your distribution. Generally, if you have a higher variance, you need to go to a higher order. And so let's say we have a log normal distribution with a mean 5 and a standard deviation of 3. That will give us a coefficient of variance 0.6, and we perform the expansion using the formula that I presented before. We can calculate the different contribution of the different orders of polynomial chaos and their combination of to such a log normal distributed random variable x. And here I'm showing you the the effects of different orders of polynomial chaos to the random input. As you can see here, the PC order 1 will give us a normal distribution, a Gaussian distribution. This Gaussian distribution might have the same mean and a very close enough variance to the original input, but you can see in terms of the tail distribution, in terms of the form of the distribution, it's totally different. And once we increase the order of the polynomial chaos from the order 1 to order 2, you can see it becomes better. At least now it kind of captured the property of the positive definite, but they still have a quite a significant difference. And it turns out that in this case, we need to use polynomial chaos up to order 4 to accurately capture the distribution of such a log normal distribution. So as you can see here, we have a standard deviation of 3, which will give us a coefficient of variance 0.6. So how about we increase the standard deviation from 3 to 8, and that will give us a coefficient of variance 1.6. So this is a lot of uncertainty for this random variable. You might not encounter such a larger uncertainty in the in the practice, but here at the illustrative example, we also calculate the different contribution of different orders of polynomial chaos to such a random variable. And as you can see here, in the previous example, polynomial chaos of order 4 can already be sufficient to capture the distribution. But But in this case, even if it goes to PC order 4, there's still a lot of difference compared to the PC synthesized distribution and the original input distribution. And actually, in this case, we need to go even higher order to go to polynomial chaos order 7 to capture the distribution. And lastly, we show an example of also commonly used gamma distribution. And and in this case, you can see here the gamma distribution, we need to go to up to order 3 to capture such a positive definite gamma distribution. And so previous, I already presented how to do the Hermite polynomial expansion for a single random variable. And so how about when you have a bunch of random variable, which is, for example, our generalized random field, we will do the same thing, Hermite polynomial chaos expansion at each individual location of this random field. But now instead of we having a deterministic polynomial chaos for each specific location, now we have a deterministic polynomial chaos field, polynomial chaos coefficient field for all these different locations. And instead of having a standard Gaussian random variable as the basis of to construct the Hermite polynomial chaos, now we need to use this underlying Gaussian random variable, Gaussian random field. Essentially, this becomes a zero mean unit variance Gaussian random field to construct the Hermite polynomial chaos. And the function form of the Hermite polynomial chaos keep the same. It still have the zero mean and the property of the orthogonality. And we can also choose some orders to quantify the any types of marginal distribution of this at each individual location. But another important thing is missing, which is the correlation structure. So we also need to considering the correlation structure of the original generalized random field. And for that, we still need to do the Cahulian-Loiva expansion to capture this correlation field. And we will talk about the Cahulian-Loiva expansion in our next lecture. And with that, I would give thanks to my collaborators and funding resources. And this Hermite polynomial chaos expansion has been implemented in real ED simulator system. So you can check out. Yeah.
Thank you very much. So we'll stop here. I'll stop recording again. This is all in part of Real Easy. It's documented and so on. So please feel free to check it out. So we'll stop here. We'll continue with next lecture. Let me stop recording.